Last time we started talking about undecidable. Ooh, that's the wrong chalk. Undecidable languages. And we proved that the halting problem is undecidable. Well, that's another way of talking about a specific language, which was called ATM. So let me just remind you what that is. ATM is the set of input where the first part of that is a description of a Turing machine, and the second part is some specific input, and then such that M is a Turing machine that accepts input W. Okay, so this is a language. Remember, a language is a set of strings, and each string in that language has this form. It's a description of a Turing machine with some specific input. And the language consists of those strings such that M is a Turing machine that accepts W. And we proved last time that this is an undecidable language. There's no Turing machine that can decide this language. There's no Turing machine that can take in input of this form and accept or reject whether that string is in the language or not. Okay, so this I was saying was one of the high points of the course, the proof that there are undecidable languages. There are problems that cannot be solved by a computer. The problem of taking in a description of a Turing machine and particular input and having another computer or another algorithm look at that string and decide whether or not that Turing machine M accepts W. So you can actually prove that such problems are unsolvable. And I don't know about the rest of you, but I was elated. This is like one of the high points for me of teaching this class is when I can show this proof, and the glow lasted for a couple of days. Don't worry, it's worn off. But I hope some of you appreciate what an amazing accomplishment of human deduction this is, that you can actually prove, not just have an opinion or just have empirical evidence, but actually have a mathematical proof that there are certain things that are undoable by, in this case, by an algorithm or by a computer. There's often an expression that people say, you can't prove a negative. That's just not true. You can often prove a negative, and we do frequently. And here's an example of proving a negative. Okay? Has everybody heard that expression, you can't prove a negative? If you want to show something exists, you can show it. I mean, there's a way of establishing it by just exhibiting it, if you happen to have it. But to prove that something doesn't exist, well, a lot of people would say that can't be done. That's something that can't be done. But here's an example of proving a negative, which is kind of ironic because they're saying they have a proof that, anyway, for a moment my brain went in a little spin there where there seemed to be something ironic to point out, but now I've lost the moment. At any rate, I just want to emphasize that in the 20th century, that was the previous century, there were four big ideas that came from deduction. There are lots of other scientific accomplishments, but there are four that are sort of considered as jewels of deduction. And one of them is relativity theory. How many people have studied special general relativity? Nobody? A few of you. Well, you should. It's just, especially special relativity, is really simple if you know just basic Newtonian physics and the Pythagorean theorem from high school. You yourself can derive E equals mc squared by just simple considerations. So that's pointed to as one of the great jewels of deduction in the 20th century. The second one, I mean, I'm lumping together special and general relativity. And the second one is the idea of quantum theory, which also was basically a deduction, both tempered by experimental evidence, but sometimes afterwards. And then the third one that people point to as being one of the great deductions of the 20th century and one of the mystical things that only a few people can understand, which is not true at all, is what I mentioned last time, Gödel's theorem. And Gödel's theorem proves that there are, among other things, it proves that there are true statements about arithmetic, true statements just concerning plus and multiply over the natural numbers that are not, they're true, but not provable. So, there are things that you can state about arithmetic that's true, but nobody can actually prove it. And then the fourth one is Turing's theory of undecidable languages and undecidable problems. And and this is actually quite related to Gödel's theorem. And in the book, there's a brief introduction to Gödel's theorem and even a little bit of a sketch of Gödel's proof. But if you understand how this proof goes, and then you can if you then understand the context of Gödel's theorem, the actual proof of Gödel's theorem follows the similar lines to what we did here last time. We did this in 15 minutes last time. When we finally got to the proof of this, it was just a simple little self-referential conundrum that in the end forms a contradiction and a proof. Okay, so I want everybody to appreciate that you've just been exposed to one of the great mysteries of the 20th century. There was a time when people said, there were only 5 people in the world who understood relativity. Well, that was, of course, silly. There was a time when there was only one person, but then once it was disseminated, there were many. And similarly, it was said there's only 5 people in the world who understand Gödel's proof. Well, that might have been true because the original paper, Gödel's paper, was very, very hard to read. And it was in German, so, that made it harder. But now that the essence of that has been distilled and simplified, it's not that hard. And what we did last time with Turing's theorem on the halting problem is really not that hard. Okay, so today what I'm going to do is prove this again with a different approach. So last time we did it with a method that I called self-reference. And today I'm going to do it with a method called diagonalization, or diagonalization. Yeah, diagonally, you have to say that right, otherwise you go someplace weird. Okay. How many people got that reference? Thank you. At least a couple of people. All right. Anyway, there's diagonalization, and they're related in some ways. And the world seems to be divided into 2 types. There are the people who think this is the simpler way of doing this, and there are people who think this is the simpler way. I find self-reference very confusing, and maybe some people did. And diagonalization is simpler, but other people have a different opinion. So I'll do both. Okay, but before I get to diagonalization, I want to go back a little bit and emphasize where we are in terms of the conceptual framework of where we are. This relates also to your homework 6, which I guess is the due date is today, but of course you have the extension time. And most of that homework, or many of the problems in homework, ask you to prove, language, some language, just call it L at the moment, is decidable. Decide, I guess there's a D in there somewhere. Decidable, okay? And you have to take the right conceptual level in order to tackle this. Okay, so this is asking for, let's actually take, what is it called? A DFA. Okay, so A DFA is the set of, we're given a DFA M W such that M is a DFA and M accepts W. Okay? So this is not, in order to show that this is decidable, you don't want to focus on M and show how the DFA M can decide W, whether W is in the language or not. What you have to do is have a Turing machine that it has input M and W, a description of that DFA and the input W, and okay, let's give a name to the Turing machine, M prime, and M prime has to decide if the DFA M accepts W. Okay, so you have to focus on the Turing machine that takes in the description of a DFA. All right, so that's a different level of abstraction, a different level of attack. Now, in this particular problem, what does this Turing machine M prime do? Yeah, I heard the word simulate. Yeah, it simulates M on W. Okay, so this one isn't so mysterious or difficult to think about. Okay, but now let's take a different one. Let's take all DFA, which I think is on your homework. And by the way, what is the actual symbol that's used for a DFA in the homework? Do you know? Does anybody remember or have it in front of you? Oh, well, I'll call it M. M accepts all strings. Okay? So now simulation doesn't make sense anymore for this problem, because what would you simulate? This is a question about all possible strings. Okay? You can't simulate this DFA on all possible strings in order to make a decision about whether the DFA accepts all strings or not. Okay, you can't get your Turing machine that takes in that. That Turing machine cannot take in the description of this DFA and then start generating input and testing each input to see whether or not the DFA accepts that input or not. Okay, so that would be thinking too low a level. Instead, this Turing machine M prime has to have within it some idea. You have to give it some idea and encode it in the Turing machine that allows it just to look at the description of this DFA and therefore decide yes or no, accept or reject, if M accepts all strings. Okay? And so you have to think about how you, if you were given a DFA, would look at that DFA and decide whether or not that DFA accepts all strings or not. But once you see the idea of how you might do it, then you have to encode that idea into a Turing machine that can do that same thing. Okay? But my main point is that this is a more abstract question than whether or not a particular DFA, accepts a particular string or not, okay, or even whether a particular DFA accepts all strings. Okay, if I show, one problem would be I show you a DFA and I say, does this DFA accept all strings? Okay, you can look at that and you can figure out yes or no. Okay, but that's a lower level question here than saying, build a Turing machine which can be given any arbitrary DFA, and that Turing machine has got to be able to decide whether that arbitrary DFA accepts all strings. Okay? So I just emphasize this because in office hours this week, I could see there were some people who were not getting the context of the problem, the context of what it means to be decidable. That it is a more high-level and abstract question. Now, I was trying to think of a good analogy to make this distinction clear, and I didn't succeed, but here I'll give you a bad analogy. Maybe people will understand anyway. So let's say you have some candy machine, okay? And it has, various types of candies, Mars bars or whatever. And it's got a place where you put in the money. Okay. And you might ask, does this candy machine work correctly when I put in the money and I ask for a Mars bar? Okay. Well, that's, or even I'll simplify it. Does this candy machine work correctly the next time I put in the money for a Mars bar? Okay. Well, how would you answer that question? I mean, you put yourself in the position of you're the service person for this candy machine, and you want to know, does this candy machine work correctly? Or will it work correctly the next time somebody wants a Mars bar? What would you do? Well, somebody's got to know. Come on. There's 64 people there. What, you do what? Yeah, you put in the money, try the thing, and see if it works. Okay, you get yes or no. The thing worked or it didn't work. All right. So that's a very specific low-level thing, and this is a specific, let's say this is a specific DFA, and you have a specific input or question. Will it work when you, W is sort of the question of will it work the next time somebody wants a Mars bar? Okay, so you have that question. But we could have another question, which is you're just given the machine. That is, you're given the candy machine, or machine candy if you speak French. You're given the candy machine, and you're asked, will this machine always work? Okay. Well, actually, that's a very simple question. What's the answer? We all know the answer is no. But, okay, besides that fact about real-world candy machines, the point is that this is now a question about an infinite series of events, of future events. It's not just talking about will this candy machine work the next time somebody wants a Mars bar. It's will this machine always work, okay? And that is a much more abstract and high-level and difficult problem, okay? And that's more akin to what we're doing over here, where I'm in this, this kind of question about DFAs. There's an even more abstract step here, which is that here I'm saying the machine is specified, and the next task is, so let's say, okay, you're the service person, and you know how to check whether the Mars bars will work the next time. Okay, that gives you some level of competence. But this is you're even better. This is the particular machine that you have to maintain on the 3rd floor of Kemper Hall on the south side, and you have the technical know-how to be able to decide whether or not that particular machine will always work. That makes you a more skilled kind of person, right? But even more skilled than that is if you're the person who can take in any arbitrary candy machine, and be able to decide whether or not it'll always work. Okay? So your skills are not just honed for this particular candy machine in this particular location, but you have general skills that somebody, they can walk up to you and say, okay, here's the description of this candy machine, or here's a new candy machine you've never seen before. Now tell me if it will always work. Okay? So that is the right abstraction level to understand problems like this. Okay? So you would like to be that person, right? That gives you more skills and more pay and more respect and so on. And that's the kind of Turing machine we're talking about. Does a Turing machine like that exist or not? Okay. Does a service person exist who can always take in a description of it, or be given a new candy machine and decide whether that candy machine will always work or not? Okay. So when you see this language, prove L is decidable, for languages like this, we want a Turing machine M prime. We want that super candy machine maintenance type person who can figure out whether the candy machine will, that new candy machine that's never seen before, always will work. And here we want to know whether we want a Turing machine that can take an input of a DFA and decide whether that DFA accepts all strings. Okay? All right, well, that was about DFAs, and that's on your homework. Okay? But now, in terms of this language, what is it that we want? We want a Turing machine that has input. Actually, I'm going to phrase this a little bit slightly differently. A Turing machine M that has input of another description of another Turing machine. And M prime has to decide if this Turing machine halts on every input. Okay, that's different than this problem, but take this particular abstract problem. We want a Turing machine M prime that can take in a description of any other Turing machine, okay, and M prime has to decide, say, accept or reject, that M halts on every input. And again, you can't just have M prime simulate M. We know how to build a Turing machine that can simulate another Turing machine. Okay, we talked about that last time. That's a universal Turing machine. But that won't work to solve this problem, because this is a problem about every possible input. Okay, so this is like that candy question. This is a new candy machine that's never been seen before. Okay, that hasn't been built into what M prime does, and M prime has to decide if it works, or in this case halts is the analogous thing, on every possible input. Will the candy machine always work? Okay, and just as the candy maker, or the guy who's looking at any new machine, can't just test that machine forever to make the decision, the Turing machine M prime can't. Okay. Now, what do you think about this? Let me give this a name. I'm sure I know that there is a name for this. I just don't remember what it is. But let's call this. Well, anyway, do you think this problem is decidable? Do you think? Let's just put it. I'm lapsing into some jargon that you haven't fully explained. So let me just say, do you think such an M prime exists or not? Yeah. Who said yes? Yeah, why?
Well, with just a guess,
Okay, good. You got there eventually. Yeah. No, this is yet another problem. Well, this is the second one we've seen. A problem which you can prove there is no, well, let's put it this way. We can prove that there is no such Turing machine M prime that can decide this problem. Okay? So I should have, the reason I'm getting myself in a sort of a linguistic or grammatical jumble here is because we've always talked about languages, and a language is a set of strings, and a string is in there or not, and a Turing machine accepts or rejects a particular string. But all of a sudden I've gone over to this language of problems, and I haven't fully made that formal connection here. So if I phrase this as a language, so L is equal to a set of Turing machines such that M halts on all input. Okay, then this is a language. It's a language where the strings are descriptions of Turing machines. And then we can ask, is L decidable? Okay, so now this question is properly formed in terms of what we've been talking about in class. So is this language L decidable? And that is there a Turing machine M prime that can take in any input M, which describes another Turing machine, and M prime decides if M halts on every input? Okay. All right. Well, again, having hopefully framed the questions properly so that you see what a high level we're dealing with. And again, maybe another metaphor or analogy. Imagine you're a doctor, okay, Dr. Turing, okay, and you have a particular patient comes in with a particular set of symptoms, okay. You can maybe cure that person for those particular symptoms. And so that's the low level, sort of a particular person, that's a particular Turing machine that the doctor is seeing with a particular set of symptoms, that's a particular input for that person. And that problem is different than if you're a medical researcher and you're asked, find a cure for the following set of symptoms. So anytime anybody has those symptoms, you have a response that will always cure them. Okay. It's just a different level of attack as opposed to being the doctor on the ground or the researcher who's thinking about the whole big picture. So these questions about decidability deal with, is there a Turing machine that can do the big picture, answer the big picture problem? Okay. Well, all right. So let's get to something technical. All right, I want to prove again that this particular language is undecidable. All right? And I want to use a technique called diagonalization. So let me say a little bit about diagonalization. How many people have seen diagonalization in some other context? Okay, a couple of you. And in what, a logic class or set theory? In what?
ECS 20.
Oh, 20, yeah. I suppose they would have done that there. Okay, so diagonalization was actually introduced by Cantor, I don't know, in the 1700s, 1800s, I don't know exactly when, who was trying to think about different sizes of infinity. Does that make any sense? I mean, infinity is infinity. How can one infinity be bigger than another infinity? Okay, my infinity is bigger than your infinity. But he got to thinking about that and ended up with the following formalization. Two infinite sets are the same size if and only if you can form a one-to-one and onto correspondence between the sets. So you have one set which happens to be infinite size and another set which happens to be infinite size, and you can describe a way of finding a pairing between elements between the two sets. One-to-one means that this mapping or pairing never pairs any single element with more than one. Okay, we don't have this kind of pairing going on, where this is paired with these two, and anyway, this one is paired with that. That doesn't exist. You just have each element, any element in here is paired with exactly one other element in there, and each element in here is paired with exactly one over there. Actually, I said that too strongly. It's paired with no more than one. And onto means that everybody is in the show. Everybody is paired with somebody. So this is just often called one-to-one correspondence or correspondence. Okay? So every element in here is paired with some element over there, and every element over here is paired with some element over there. And you get to describe how to do that, but remember these two sets are infinite, so you can't actually write out the actual correspondence. What you do is you describe how those elements what the correspondence looks like. You can't actually ever finish writing it out. So, for example, the example n is the set of natural numbers. That means 1, 2, all the positive integers. Okay? And notice this is natural. Okay? For those of you who thought that numbers began with 0, because you program in C, or some other language like that that has that hideous convention, that's unnatural, okay, in my opinion. This is just a chance to rant about somewhere along the line somebody decided that the numbers should begin with 0, and arrays in C are indexed at 0. I mean, it's an abomination, but okay. Natural numbers begin with 1, as any sane person knows. All right, the set of all natural numbers, and the evens, even numbers, well, that's 2, 4, 6, 8, and so on. Well, they're both infinite, right? And at first glance, it looks like this is a bigger infinity. This is a bigger infinity because every element in here is in there, and yet there's some elements in here that are not in there. Okay? But according to Cantor and according to this definition, the two are the same size. Okay? Because you can find a one-to-one and onto correspondence between the two sets. You just these are the numbers in n, 1, 2, 3, 4, and these are the even numbers, okay, 2, 4, 6, 8. And this correspondence, so in general, if you have an n, it corresponds with 2n. So I've described a one-to-one and onto correspondence. Every natural number corresponds to some even number, and not to two even numbers, just to one. Every even number corresponds to exactly one natural number. And even though this goes forever, down to the bottom of the Earth and beyond, I'm not sure if I go down that way where we get to on the Earth, and if we go beyond that, I'm not sure where we get to in outer space. But at any rate, it goes forever, but this correspondence works forever. All right? So there is a way of corresponding, of finding this one-to-one onto correspondence between the natural numbers and the even numbers. And so according to Cantor's definition, these two infinite sets are the same size. All right? Let me give you another example. Q m over n, such that m and n are in, they're natural numbers. M and n. So these are the rationals, right? The rational numbers. So can I put the rational numbers in one-to-one correspondence with the can I put the rationals, maybe I said that. Can I put the rational numbers in one-to-one correspondence with the natural numbers? I have one no and one yes, and one not responding in between. Makes a perfect, yeah. What were you saying?
Also, where are you supposed to start with your bijunctor, your one-to-one and onto correspondence with Q onto N? Like, where are you proposing to start?
Well, okay. You're right that I have to, if I want to say that there is a one-to-one and onto correspondence, I have to demonstrate it. Okay, and it may not be obvious how to do it, but absence of evidence is not evidence of absence or whatever. So yeah, so it's not obvious how to do it, but doesn't mean it's that by itself doesn't mean it's not doable. And you had a suggestion?
Yeah, you go like 1/2, 1/3, 1/4, and then below that you go like the next one down to like 2/3. Then you go diagonally.
You've seen this before. You've seen this movie.
Yeah.
Okay, all right. Yeah, yeah. He knows the punchline. Okay. Spoiler alert. All right. Yeah, so let's try something. First of all, we'll just look at what the rationals are. We have 1, 2, 3, 4. I'm building a table here. Go to 5. And so these are the natural numbers, and they keep going forever. And then we'll look at the rationals. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. And then this is 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, etc. Like that. It's 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5. Okay. Now, every rational number is here because that's what a rational, it's the ratio of two natural numbers. And so here we're talking about the numerator, here's the denominator, and definitely in this two-dimensional table, which goes to infinity in both dimensions, it goes to infinity that way and to infinity that way, definitely this contains all the rationals. Now, each particular rational may be there many times. In fact, it's going to be there an infinite number of times. Like the number 1, it's there as 1 over 1. It's also there as 2 over 2 and 3 over 3. Okay, so, but that doesn't matter. This certainly contains all the rationals, even though each particular rational is there many times. Okay, now, if I want to claim that the rationals can be put into one-to-one and onto correspondence with the naturals, the rationals with the naturals, I have to exhibit some kind of a one-to-one and onto correspondence between them. Okay? So what is sort of the most obvious correspondence to try? I could try, let's say, row-wise. I could say, okay, this rational is going to correspond to number 1, natural number 1. And this is going to correspond to natural number 2. And this is going to correspond to natural number 3. And this is going to correspond to natural number 4. And this to 5, and this to 6, and so on. Okay? And say that's my correspondence. But then What about the numbers in the next row? What do they correspond to? Because in the first row, you're going forever. You're saying these guys in the first row correspond to the natural numbers, and that correspondence goes forever. So there are no natural numbers left over for the second row. Okay? So that way of showing a correspondence isn't going to work, because you take a particular rational like 3/4, okay, and 3/4 never shows up in the first row. First row has a numerator of 1 always. Okay, so 3/4 isn't in there. And if you say this correspondence is going to be 1, 2, 3, 4, and that goes forever, you never get down to the next rows. Okay? And so 3/4 wouldn't be in your claimed one-to-one correspondence. So it wouldn't be a one-to-one correspondence between all of the rationals, because 3/4 should be in there, and all of the naturals. Okay, because all the naturals are used up here. Infinity is a funny thing. I mean, anyway. And just sort of as a side note, 2/4, we don't have the same problem with 2/4, okay? Because 2/4 is the same as 1/2, and 1/2 is in there. So some of these rationals would be included if I just focused on the first row, but others are not, in particular 3/4 would be in trouble. What other ones from the second row are a problem? Which other ones from the second row, just in terms of what I've written up here, would not be there? Yeah, this one is not there. Okay, what about this one? It is there because that's the same as that. And 2/3 is not there. This is there, and 2/5 are not there. Okay. All right. Okay, but you proposed a different way of doing the one-to-one and onto correspondence. And what was that?
You go on diagonals.
Not quite. You go on the anti-diagonals. Okay, so the way I want to do a correspondence between the natural numbers and the rationals that is sure to get all the rationals is to order the rationals this way. This number is going to be associated with 1. And that I've completed that anti-diagonal. And then I'm going to move on to the next anti-diagonal. And this number is going to be associated with 2. Not because it is 2, but because it's the second natural number. And this number is going to be associated with 3. Okay? And then, having completed that anti-diagonal, we move on to this anti-diagonal. And this number will be associated with 4, this one with 5, and this one with 6. Okay? And then we go into the next anti-diagonal. This will be 7, 8, 9, 10. Everybody get the idea? We're going one anti-diagonal. All right. And so you should see that using this method, every number in this table eventually gets included. Okay, no matter where you are, no matter how far down you are in this table, when I go by anti-diagonals, eventually I get down to it, because no anti-diagonal is of infinite size. The anti-diagonals each have a fixed finite size. That's the neat thing about them. The size of the anti-diagonals get bigger as I move down, but none of them are infinite. And so eventually, for any particular square, for any particular rational, here we're looking down at, for example, 16,017 over 14,058. Okay. That particular rational eventually gets included in some anti-diagonal, right? And we're just associating the elements with the natural numbers 1, 2, 3 in order. So I've demonstrated that I can put the rationals into one-to-one and onto correspondence with the naturals, and therefore those two sets, although they're both of infinite size, have the same infinite size. Okay. All right. So that's in order to explain what it means for two sets to be the same size. And there's a definition that we want to use. A set that is either finite or can be put in one-to-one and onto correspondence with the natural numbers is called countable. So what we've shown is that the rationals are countable. The even numbers are countable. What about the natural numbers? Are they countable? The natural numbers? Yeah, of course. The natural numbers are countable. It can be, the natural numbers can be put in one-to-one correspondence with the natural numbers. So it's, and what's the correspondence? Well, yeah, each number corresponds to itself. Okay, I'm just exercising the definitions here. Okay, it was a trivial question, but it had some real meaning. Okay. So now I want to show you a set that's not countable. And by the way, this is not, when I spoke earlier, there's this technique called diagonalization. This is not the diagonals of which we are speaking. Okay? The diagonalization comes right now. So now I want to show you that the real numbers are not countable. Okay? The real numbers are not countable. Okay? So what are the real numbers anyway? How do they differ from the rationals? They what? Are you who's speaking? Oh, way back there, sorry, yeah. They include the irrationals. Is that what you said? That's true, rational plus irrational. But something else that's sort of, well, and what does irrational mean?
Well, you cannot express it as a fraction.
You can't, yeah, you can't express it as a fraction of two integers or two natural numbers. Okay. And what else? Oh, okay, anyway. Certainly, anyway, the key point that I want to say about the reals, but actually it's also true for the rationals, so is that you have numbers that have, if you write them out in decimal, they have numbers that include an infinite number of digits. Okay? Although that's also true for some rationals if you write them as in decimal form. But that doesn't matter because you can also, a rational can always be written as the ratio of two integers. And here we're seeing that because of that fact, the fact that you can write them as the ratio of two integers, we can do this nice one-to-one correspondence. And now, if we think about the reals, and they can't all be written that way, so we're going to write them down in the following way. Well, the proof here is suppose the reals, usually written like that, are countable. Countable means there is a one-to-one and onto correspondence. Correspondence between the reals and the naturals. Okay? So imagine that there's a table that shows exactly what that one-to-one and onto correspondence is. So here's the natural numbers, 1, 2, 3, 4, 5, 6. They go forever. And here's the corresponding rational. Okay, this is in the claimed one-to-one and onto correspondence. So there's some rational number that's in one-to-one, that's in correspondence, that's mapped to number 1. Okay, what is that? Well, yeah, we don't know. But just for illustrations, I'll just make up one. Okay. Can anybody complete this one for 3 billion digits? Somebody can. It just announced in the newspaper the other day. Okay, so here's one particular rational number, and it happens that the digits go forever on this particular one. Is this, by the way, did I do this right? Anybody recognize this?
I think family node to 5 decimal places.
How many?
Family node to 5 decimal places.
Okay, but was I right? I think that, okay. All right, anyway. And then the next one is, I don't know, 55.5, and that goes on for a while. And next one is 0.3. The numbers don't really matter. Okay, and so we're going to write these all out with infinite digits, even if they're just all zeros. Okay, afterwards there. All right. So the point is that on the assumption that the real numbers are countable, there has to be this correspondence like this. Now, to prove that they're countable, you have to describe a correspondence, just as we did for the evens and for the rationals. But here we don't have that explanation because, in fact, they're not countable. But still, there would be such a table if there is such a one-to-one and onto correspondence. So we can conceive of this. All right? Now, I'm going to do the diagonalization. Diagonalization will create another rational number, another real number that I claim is not in there and cannot be in there. Okay? So diagonalization I'm going to create a real number, call it x, where the ith digit of x after the decimal point is different from the ith digit after the decimal point in where? In the number in the real numbers that corresponds to natural number I. Okay, so this is the number that I'm going to create. And let me just do this in terms of this example. So you claim that there really is such a correspondence. And now I'm going to say, well, think about the following number. It's going to be 0 point something. The first digit, for the first digit after the decimal point, I'm going to look at the first digit after the decimal point that of the real number that corresponds to natural number 1. Well, that digit is 1 there. So what I'm going to make this one is anything other than 1. Okay? And for a technical reason, I'm going to not make it 0 or 9. But that still leaves me 8 choices or 7 choices, right? It can't be 1. If I exclude also 0 and 9 for some technical reasons that I'll get into later, I still have 7 choices left. So maybe I'll make it 3. Okay? And then the next one, let's say this 5 had a 6 after it. For the second digit here, I look at the second number in this correspondence, or I conceive of that second number in the correspondence, because this is a proof. It says a proof if there was such a correspondence, then I'll look at the second number in the correspondence and the second digit after the decimal point there. This is a 6, so I'll make this anything but a 6 or a 0 or a 9. Okay? It could be like a 4. And the next one, let's go out here, 3 digits. Let's say the 0.3178. Okay? So this one, I'll make it anything other than 7 or a 0 and 9, maybe a 5. Okay? And then the next one is a 0. Okay? So maybe I'll make that a 1. Right? Or do I have to avoid 1s? I know. Anyway. I'll tell you about the degeneracy later. But let's exclude 1s also. We still have plenty to choose from. Okay? And so that's the number I'm conceiving of. So this is a proof. So proofs have things in them that you can't actually physically write down, but you can conceive of. We can conceive of that there's this one-to-one and onto correspondence between the naturals and the reals. And then we can conceive of this number x, which is defined with respect to the supposed one-to-one and onto correspondence. Everybody with me? Now I can ask, is x in the table? In this table. This table is supposed to have all the real numbers. Every real number corresponds to some natural number. Okay? Every real number, there's an infinite number of real numbers, but they're all supposed to be in this table somewhere. And the question is x, first of all, is x a real number? Yeah, sure. I mean, yeah. Okay. It has a well-specified, if I do this thought experiment forever, I could even have a specific rule. My specific rule is whatever digit here is in the ith position, the one in x is going to be I plus 1, unless that happens to be 9 or 0 or 1, then I'll make it, unless it, whatever. I can give a specific rule so that you're absolutely convinced that this number exists, even going for infinity. There's a rule that tells you what this digit is going to be out here, no matter how far you go out. So this number exists. It's a real number. But is it in the table? Well, who says it's in the table? Anybody says you say it's in the table? Where in the table?
Somewhere.
Somewhere.
Far enough you'll find it because it's enumerated against the natural numbers.
I didn't hear what you said.
You may have to go down a long way to find it, but the beginning of the proof had us suppose that the real numbers are countable, so we know it's got to be in there somewhere.
Well, okay, the proof supposed, but a lot of supposition, a lot of proofs where we suppose something, and then we come to a contradiction in the proof. We come to something which contradicts the supposition. Then the resolution of that is to say that the supposition wasn't true. And then that becomes the proof. So here we're supposing that the real numbers are countable, and then we'll come to some point of a contradiction, something that is either contradicts that initial supposition or contradicts some other thing that we know to be true. And then we have to conclude that the original supposition was false. Yeah?
You won't ever find it, right? Because the way you constructed it, you based it off of what was in the table.
Okay, so you're voting that no, it's not in here. Yeah, I'm with you. Okay, and here's the reason. So you say, somebody says, X is definitely in there. So I say, where? It's at position, 205879. Okay, so we go to that point in the table, and I look over to digit 205879 after the decimal place. That particular digit, let's say it's 8, and I look at that digit at position 205879 after the decimal place, let's say here, that digit will not be 8. By the rules of how X got constructed, that digit can't be 8. It might be 7. Okay? So definitely, this number, the real number that's written here, is not equal to X. And that is true for whatever place in the table you say X is. So whatever claim you make about, oh, well, X is down here, I can say, no, it isn't. Yeah?
Couldn't you use the same argument, though, for the set of natural numbers being countable? Like, you just keep adding numbers to the end forever? Like, so for one first number, the set would be 1. So you choose something different. So you choose 3. And then for 3, the second digit out is no digit. So you just add a number. And then so on forever. So you'd have this infinitely long number. You know it's still in the set of natural numbers, but by using that argument, you could argue that the set of natural numbers is not countable.
You're the same one who argued that, that ATM was decidable. Yeah, that weren't you? It's good thinking. Yeah, that threw me for a loop for a while too. We'll get back to that one. But now you're arguing that the same argument that's used here we could use to prove that the natural numbers are in fact not countable. But of course, we already know that.
They are.
Yeah, so we'll try to write that out in a minute and see where that seems to go wrong. Okay, but it's a good thought. I appreciate that. Let me just first finish with this and then make sure everybody understands what this is doing. And then we'll see what seems to be the problem with the natural numbers. Okay, so anyway, does everybody get this? How this worked? That we suppose that there's a one-to-one correspondence between the naturals and the reals, which means there has to be a table like this. Okay, but if there is a table like this, we construct another real number, x, by the diagonalization idea. This is where the diagonalization comes in. We're diagonalizing. It's the ith number, or the ith row in the table, and the ith digit here after the decimal place. And so we're going down the diagonal, and we're changing the value, setting the digit in x to be different than the digit in what we're seeing here. And for technical reasons, I'm going to avoid 0, 1, and 9. And that's just because 1.99999 is equal to 2. This goes forever. Kind of an annoyance. But the point is that suppose you had 2 in the table, and, well, actually, this is not just changing things. Okay, so this is equal to 1. Okay, suppose you had 1 in the table, and you changed it, you made x equal to that. Okay, these are actually the same number if you believe in infinity and mathematics and all that stuff. So just to avoid any of those kinds of degeneracies, I'll just not use 9. And I think I'm worried that we could get into similar problems with 0. Okay, at any rate, but back to the main point. The main point is now I've created this number x, which is not in that table, and therefore this correspondence is not one-to-one and onto, and that means that the real numbers are not countable. That's how that proof goes. Okay. What? Oh, I guess that came from next door. All right. I want to leave enough time for the midterm, but okay. So I'm going to try to deal with your question. We're not going to. I can see that with the return of the midterm, we're not actually going to get to this today, but I will show you a proof of this, that ATM is not decidable by using a diagonalization idea. So all of this, what we're doing today, is preparation for that proof. But let's look back at the naturals and see if we can get out of this trap. So, okay, a student posed question. Can't we use this to show that the naturals, that n is not countable? And I think what you had in mind was, well, here are the naturals that we want to do the correspondence with. And then there's some way we're going to do a one-to-one correspondence. And it doesn't have to be the most natural one of 1 corresponding to 1, 2 corresponding to 2, and so on. But there's going to be some natural number that's written here, 3, 4, 5, 6, 7, 8, 1, 1. Okay. And then there's going to be some natural number that's written here, 36, 40, 485, 907, 95616, 753, 860, whatever. Start enumerating phone numbers. Okay, so there's an enumeration like that. That's what it means to be one and onto. And then you want to do the diagonalization. You want to create a new integer, I. Create integer I that is not in the table. Okay, so we'll do the diagonalization. The first digit of I should be something different than 3, right? So what do you want to make it? 7? Okay, so 7, I equals 7. And the next one should be something that's not 6. Okay, so, okay, lucky 7. I'm going to, just to shorten this a little bit. And the next one should be something that's not 5, right? And what do you want to make it?
2.
Right, 7. No, 2. Okay. And the next one, we look at the fourth. It's the fourth entry, and we look at the fourth digit, but oops, there's no fourth digit. Okay, yeah.
I don't think every ordering has to correspond.
No, not every ordering. This is just.
Some ordering exists, so we prove that some ordering exists.
Yeah. I just said suppose this is a correspondence. Okay. For the natural numbers to be countable, I mean, we already know they are by definition, but there should be some correspondence between the natural numbers and the natural themselves. Okay? And I'm just saying, suppose this is one. Then we'll do this diagonalization. I could have looked at 1 with 1 and 2 with 2 and tried a diagonalization there, and we'd see even sooner what the problem is. Yeah.
I guess wouldn't you want to actually go the other way, like move away from the radix point, like going to the left, so that you would start at the 1 spot, and then in the 10th spot, and then in the spot, go out like that, like in your method here, instead of going forward.
Okay, so well, let's get there. But let's see first what's happening, what's failing here. So what's failing here is we try this diagonalization, and we get to a point where there's no digit in the required position. Yeah.
Well, if there's no digit, then couldn't you just put any digit? And as long as there is a digit in that place, then you know it's going to be different because that has nothing there. And if there is something there, it's a different number.
Okay, so now I'll
So you can just add anything there. It's a free space.
okay, just add anything there, yeah, like an 8. Okay, and since this number doesn't have a fourth digit, then, and this number does have a fourth digit, this one will not be equal to that one.
Yeah.
Okay, yeah.
Then I wouldn't be in the natural numbers. It's infinite length.
Because what?
Infinite length wouldn't be in the natural numbers.
Okay, so here's another problem, is this is going to go forever, all right? So I, how long is I? I is infinite. Now, real numbers are permitted to be infinite. A real number can have an infinite number of digits after the decimal point, but no natural number. Every natural number has a specific finite size. The set of natural numbers, there's no bound on how big those numbers are. They have numbers of size 5, 5 digits and 25 digits, and there's no bound on them. But any particular one just has some fixed number. But here, with this diagonalization, what you're trying to do, you'll end up creating something that looks like it has an infinite number of digits. So I think we got out of that hole. Now, the other suggestion was to put a lot of zeros, an infinite number of zeros, on the left side of our integers. Okay, and it's not clear to me exactly what that means. But even if you did that, when you end up diagonalizing, you're going to still have the same problem of creating a number that has an infinite number of digits, and so it's not in the naturals. Okay, so this is diagonalization. This is Cantor's proof that the real numbers are not countable, and therefore they're a different infinity, a bigger infinity than the naturals. Okay, if you can conceive of what it means to be a bigger infinity. But anyway, technically, it means that they're not countable. Okay, they're uncountable. And next time we'll use this diagonalization idea to get back to the question about ATM and show that ATM is undecidable. Okay, and this diagonalization, I find that a much simpler way of doing these undecidability proofs than the self-reference. Okay.